everyone. Okay, this is gonna be Thursday's lessons. Hopefully you're watching it on Thursday. Okay, we're gonna talk about heats of reactions today. So, yesterday you would have done the Zoom meeting if you needed help with the mole stuff or the stoichiometry stuff, so hopefully that's all sorted for you. If it's not, again, please get in touch with me and I can help you with that. It's vitally important that you figure that out. So heats of reaction, that's what we're gonna talk about today. So all reactions involve a change in energy. So there's always going to be energy moving back and forth or forward or reverse. So we're going to call it, so again, in science, anytime we talk about a change, we use the Greek letter delta, the triangle, so delta E, so a change in energy. Now we've got two different types of reactions then. Remember, heat is the same thing as energy. Those two words are interchangeable. So we've got exothermic and endothermic. We have covered these before. So exo is heat is released, exothermic. Endo, heat is absorbed. Okay, that's the difference between them. So opposite, or two sides of a coin. So the amount of heat transferred in a chemical reaction is called the heat of reaction. Also known as enthalpy. So when you get to grade 12 chemistry, you'll have a unit where you talk about that a lot more in depth. We're just going to look at it from a mole ratio point of view for our purposes here. So we call it delta H. So again, change in energy, change in heat. So the enthalpy or the delta H is called the molar heat of reaction. So this would be kilojoules per mole for that. So there's a certain amount of heat that's either absorbed or released on a per mole basis. So it's factored into a mole ratio. So we're going to work through an example here. Number one, calculate the energy generated by the reaction of 3.6 grams of methane and an excess of oxygen. So again, we see that word excess of oxygen. So that means we don't need to worry about it, okay? So it's not going to factor in. But we're going to treat this just like we do every other dimensional analysis problem here. So what are we looking for? 3.6 grams of methane. Now, one of the things people maybe struggle with, which one is methane? So take a look through there. Process of elimination. You know methane is not water, not carbon dioxide, not oxygen gas. So we're going to put our 3.6 grams there. Now the question is asking you to calculate the energy. So my energy, question mark, is going to go under the 8758 kilojoules. So what this equation means when you write the energy into the equation like that is, well, first of all, is this exothermic or endothermic? Take a look at it. Is that exothermic or endothermic? So this is where I would get you to like talk to each other and vote. Okay, so how many of you say endothermic? How many of you say exothermic? Good, you're all right. It is exothermic, yes. So because the energy is written on the product side, the energy is produced, the energy is released. So we would say that's exothermic there. Okay, so I know looking at this that I have 878 kilojoules of energy are released for every 1 mole of methane, for every 2 moles of oxygen, for every 1 mole of carbon dioxide produced, and for every 2 moles of water produced. So you have to factor in your mole ratio when you're doing these. Okay, so otherwise we're going to treat it exactly how we would treat any other dimensional analysis problem, any other mole ratio problem. So what are you looking for? Energy equals, what do you know? 3.6 grams of methane. As per usual, I can't do anything with this as a gram unit, so what am I going to do to it? Convert it to moles, because in chemistry we always work through the mole. So grams of CH4 on the bottom, moles of CH4 on the top. In 1 mole of methane, I've got, I'm going to go 12 plus 4, 16.04 grams of methane. And where did that number come from? The periodic table. Good. Okay. So right now I'm in moles of methane. I don't want moles of methane, I want energy. So I want that to cancel. So moles of methane go on the bottom. Kilojoules goes on the top. And I know that I've got 878 kilojoules of energy for every 1 mole of methane. So now I can go ahead and work that out. So I've got 3.6 times 878 divided by 16.04, and I get an answer of 197.06 kilojoules. However, I can only have 2 sig figs. So I have to do this, or I can convert that to, it's gonna end up being 200. Yeah, those ones are awkward. Kilojoules, probably easier just to leave it with the bar on top there. Good. Any questions on that? If there are, you should be emailing me or asking me, right? Okay, so we're gonna do another example. So the next one, the combustion of 2.4 grams of octane. So given the combustion of 2.8 grams of octane. So octane, you're given the equation C8H18. Now it's a combustion reaction, so right away you know that it's plus O2, going to be coming CO2 plus water. That is standard for a combustion reaction. Make sure you're able to do that. And then you would be given the amount of energy, and it's 10,148 kilojoules. Now I'm just gonna balance this real quick here from my notes. So 25, 16, and 18. Okay, so that's balanced for you here. Now again, which one is octane? That's not naming that you're familiar with yet. We will go through that in our organic unit, which will be the last unit we cover. But we know that we have 2.8 grams here. And the question that I'm gonna ask you, energy here. So this is where I would want you to try it on your own. If you were here, I would get you guys all to work through it by yourself. So if you want to do that now, pause the video and try it on your own. See what you can get. Okay, so energy is going to be equal to 2.8 grams of C8H18. That's what you know. Your first step, always convert into grams, right? So grams of C8H18. So in 1 mole of C8, or octane, I should just say, it's going to be equal to, I'm going to cheat, 114. So 114 grams here. That number came from the periodic table. So now, I'm going to put moles of C8H18 on the bottom, because I want that to cancel. And here's going to be my kilojoules. So I know that I've got 10,148 kilojoules of energy. And this is where I would have fun, because a whole bunch of you would put the number 1 down here, except why can't you put the number 1 down here? Yes, because of the mole ratio. So you've got 10,148 kilojoules for every 2 moles of octane. So you need a number 2 there. So you have to pay attention to your mole ratio when you do that. And then you can work out your answer, and I think you end up with 106.8, so it's going to be 110. Well, I'll write it down, hold on. So it's going to be 106.82 kilojoules once you work it out, but you can only have 2 sig figs, so it's going to be here. So that's going to round to 110, kilojoules, not kilograms. Okay, now these are all very similar. You just have to read the questions carefully, make sure you're understanding what it's asking you for. So just really pay attention to things. So I'm going to assign exercise 18. There's a question that has a mistake in it. I can't remember which one now. I'll post it on Schoology and we can chat about it on there. Anyways, give exercise 18 a try. See how you do. You have the answer key, of course. Okay, take care, guys. See ya. Bye-bye.